First of all, thank you for being here in this seminar series. Today we will have three students that they will present their final bachelor's projects. So the first one to talk will be Renato Oliveira, and Renato will present its work, the work that was done in the context of KhronoSim project and the work and the experiences that he gathered using emulation in the context of KhronoSim. I think that he will give a brief overview about KhronoSim, so I won't talk about it, or at least we will provide the context for its work. And in the second talk we will have Rúben and Joel, and they will present their work in RTEMS. So RTEMS is, in case you don't know, is a real-time operating system that is frequently used in space industry. So they were doing some experiments with that operating system in the context of multiprocessor systems, and that's what they will what they will present today. So without further ado, I think that Renato can start.
Okay, so I'm Renato, as Claudio said. I'm going to present my final project in the context of bachelor's degree. Okay, so first table of contents. I'm going to speak briefly about the problem first, then about the approach that we use to solve this issue, the solution itself, and then the results we obtained, and then finally some concluding remarks which will give a little bit of context on the conclusions. Okay, so this project, as Claudio said, is part of the KhronoSim project. The KhronoSim project is a project that CISTER is collaborating with Critical Software. It's about a modular test platform that allows people to use it to develop some testing. Okay, so if you want to test several physical systems, depending on the area that we're referring to, this may be expensive. In case of aerospace systems, satellite hardware is very expensive. In case of automotive systems, the tests can be destructive if you're testing airbags or shock absorbent car parts. So also the development cycles are getting shorter each time. People need to develop faster, and this is a problem because we need to hasten this process. So we had some approaches, but the approach that we explored the most was emulation. If we can replicate the behavior of the real hardware at the functional level, we can use an emulator to test embedded systems. Otherwise, as explained, these tests can be taken into account. We can't get conclusions about the real hardware using emulation. So we defined some emulator requirements. We need a full system emulator, an emulator that is capable to emulate other architectures independent of where it runs. Meaning, if we are running a 64-bit machine, we would be able to emulate an ARM machine. The hardware is independent of the virtual hardware is independent of the real hardware. So it has to emulate multiple architectures. It has to have the adequate licensing, meaning that if we alter the emulator, the source code, we need to be able to distribute in our own terms, in the project terms. So it has to be able to emulate multiprocessor systems. We are working with embedded systems, and many of those are multiprocessor. So we have a few candidates that we studied. We have Box, Jam5, Emulate, and Kimo. So the first three did not fulfill the requirements. Either they didn't emulate in RF architectures, or they didn't have full system capacities. So we chose Kimo, which fills all the criteria that we've defined. So here are some characteristics of the Kimo. These characteristics are not all the characteristics of the emulator, but the ones that are relevant for this problem. So it's not user-friendly. It has a steep learning curve. It has hundreds of commands that you can use to configure it. So it's not user-friendly at all. It's difficult to integrate with other modules because it's, like I said, it has hundreds of commands. You can't easily use it in other modules. In this case, if we want to use it as a testing platform, as a module for testing, it's hard. And KMU executes at the maximum speed possible. This is a problem, and I will explain further why. So we divided these characteristics into two problems. So, about the first problem, we propose a library to make KMU more user-friendly and integrable with other modules. And it's written in C++, which is a good compromise between high-level and low-level language. So, okay. So this library, or as we've named it, KMU, with it we have to attend to two parts. Let's call it parts. So we have to guarantee KMU instance independence. Each instance has to be independent, and I'll explain further. And we have to study the communication with KMU. We need to, if you want to make it user-friendly, we need to be able to communicate with it in a simpler fashion than going into each virtual machine and writing commands. So, about the instance independent, this is a very important part actually. One virtual machine is one KMU instance. And the library should be able to communicate with one independent instance. That gives us more control, more fine control over our testing flux and other stuff. Okay. So about communication with KMU. Each instance, each virtual machine has a monitor. So in this monitor we can manually go there and type commands and the virtual machine will answer depending on the command. But it is separate for each virtual machine. Actually, KMU has a protocol, a communication protocol, which we can use to communicate with it. Instead of going to the virtual machine and typing commands, it's called the KMU machine protocol. It has its own set of commands, and it's a good communication, manner to communicate with KMU. We tried other approaches, which I'm not going to discuss here because it will be too lengthy. But okay, then we have another set of commands, which are the human monitor commands. So the library. The human monitor commands are the commands that you actually type in the monitor. So the library should be able to parse both of these types of commands into commands that can be sent to the instance. So it parses simpler commands. It makes it more user-friendly because some commands have lots of arguments and they're very lengthy. If we parse them into a simpler form, they will be more user-friendly. So here's the architecture. We have our KMU instances manager, which is our entry point. It's where we have all the outside interface to other modules to communicate, and it communicates with the inside components. So each instances manager manages one or more.
Show to people where.
Oh, sorry. It manages one or more KMU instance. We guarantee this independence by a unique identifier in each instance.
Don't you have the remote control, the pointer, or the pointer to
I don't think the pointer.
that makes things easier. That's a lot of information. Get it? Yeah.
No?
Or you can just use your finger. That's also good enough.
Use the traditional pointer.
Yes.
Go on.
That's good
I
enough.
will look now.
So KMU instance is a non-binary identifier, so we can guarantee the independence. It communicates through a QMP client, which is a network interface that uses TCP to send the requests and receive replies from the KMU protocol. Also, there's our parser. It's called JSON parser because the QMP protocol it's based on JSON. So we use the JSON parser to build more complex requests. So we've implemented this library. So it is now possible to provide control over individual instances, provide ease of access in configuring virtual machines. This is a problem that is more noticed if you scale your virtual machine number. If you have 20 virtual machines, you can configure them via script sent to the library, and it's way faster than going to each instance and type the same commands. Also, it's easy to integrate now because you can just compile the library to a DLL in Windows and the .so in Linux, and you can communicate with it, and it doesn't know what's inside, but it can take advantage of the feature that the library allows. So we have now solved the first problem. KMU is more user-friendly, and it's easier to integrate with other modules. but there's still a problem, which is KMU executes at the maximum speed possible. So, as I said, it runs the maximum speed at the CPU where it runs to, the host, meaning the computer running the emulator. It uses its resources to run as fast as it can. So, if we could provide a mechanism to slow down the CPU throttle and the clocks, because it's important, I will explain further ahead, we could maybe achieve a faithful replication of the behavior of the real system at the functional level. Okay, so the throttle mechanism, as we've called it, it has to reduce execution speed and reflect, more importantly, reflect these execution speed changes in KMU's clocks. So, to give some context about this throttle mechanism, KMU introduced a migration feature in version 2.4. So migration here is not migrating tasks from one core to another. It's a different context. It's migrating memory disks, an entire virtual machine to another virtual machine. You might use this to migrate one virtual machine to a virtual machine with better specs or more disk space or more RAM in order to perform the same tasks and not have to configure the virtual machine again. Okay, so in order to complete migrations, the feature has to throttle the CPU, because in case of live migrations, are migrations made with the machine still still executing. So if you don't reduce the execution speed of the CPU, you might write to the memory might get overwritten in the host machine, in the machine that you want to migrate, faster than you can copy to the second machine. So you will never achieve the full migration. You will have an endless migration. Okay. So how does this throttling work? It's actually induced by making the CPU sleep in microsecond time slices. These time slices vary according to a percentage that you configure the throttling mechanism. So we took advantage of these facts and exposed the relevant pieces of this feature to be used as a command. However, this poses some problems as we've tested. The rest of the system does not reflect these execution speed changes, more specifically the clocks. Of course, if you have clocks asynchronized, it may cause issues between the components, the hardware itself, inside that system, and if you're in the context of KhronoSim project, if you're using various systems to communicate with each other, they might have problems communicating because their clocks aren't synchronized. Okay, so how did we solve this issue about the clocks not reflecting the execution speed? We took advantage of the existing pause mechanism. The pause mechanism in KMU, it's easy to know what it does. It pauses the virtual machine. But also it has an effect on the virtual clock. The virtual clock is a type of clock that is only incrementing, only running, while the machine is actually executing. So we used pieces of this code, the relevant pieces, that actually pause the clock, and we pause this clock whenever the machine was sleeping. Let's call it sleeping. So it actually introduces a little bit of overhead. It's expected, and it doesn't pose any problems. Okay, so the throttle mechanism we implemented provides a command. Like we can type a command and the percentage that reduces the execution speed of the machine, and more importantly, this change in the execution speed is now reflected in the machine's clocks. So we've performed some studies, else we couldn't have reached conclusions. So we executed tasks in the throttled virtual machine, and we measure the real time it took to execute. So we use the client-server application. We can't measure the time in the throttled virtual machine, because even if we count the seconds that it takes to execute, the mechanism it uses to count those seconds itself, it's throttled. So we cannot actually use it to count the real time. So we needed an external agent that actually counted the real time, the task to execute. Okay, so in this case, in the case that I'm going to present here, we actually sorted a vector of 250,000 size. So we use the sorting algorithm of this complexity n times log n, and we perform the measurements. This is important.
Very high tech.
Okay, now I got my tools. Okay, so these versions were performed in a 64-bit machine. It might differ between architectures. So this is our architecture, our test application architecture. We have the virtual machine here. It creates a server. It's tested by TCP server and client. It creates a server. This is just defining factor sizes, but this is our external engine, our host, which sends the start test command. Okay, so after it sends this command, it starts measuring the real time. It waits for a response whenever it comes, whenever this guest finishes ordering, and when it receives it, it will make the math, how much seconds it actually took to execute. Okay, so here we have an example, a little bit of data that we obtained. So a task that took 1.2 seconds approximately, with no throttle, 0% throttle. At 90% throttle, it actually took 30 seconds. We measured it on the host machine, it took 30 seconds to execute. Okay, that's what I just said. Yeah, we can see so we can conclude that after 40% throttle, we can actually see in the graphic that it has a steep curve. That it's an exponential curve. So we actually made a theoretical study of the mechanism. We inserted some dummy values into it and studied how the variables compose themselves and how they relate to each other. It doesn't matter the granularity, we are using nanoseconds here, but what matters is that the curve is virtually the same. It's exponential after 40%, and we can see that our theoretical analysis corresponds to our experimental results. So we have now solved the two issues of that were presented in this project. As I said, Pinto is now easier to use and easier to integrate with other modules, and execution speed can now be controlled. Okay, so that's my presentation. Thank you for your time. If you have any questions.
So you have a question? Go ahead. So my question is more of a challenge, perhaps. I really enjoyed the presentation. I listened most of what you did. That is good. I think that work is also quite interesting. But my question is more like, if I wanted to use this KHMU to emulate some stuff, some platforms, and especially to emulate a distributed system, would it be possible, or how difficult it would be, or what would be the difficulties to have multiple KHMU instances connected to some network that I could use to pass real-time information?
Okay. KHMU actually has its own network. When you execute an instance, it has a network with the host computer. So in essence, if you execute multiple instances, they share the same network. So it should be possible. You probably can't communicate with another KHMU instance because you're isolated, but you can both communicate with the host, and you can probably synchronize communications with.
Okay, but in that case, you would be limited to when you say they are connected, what do you mean? What sockets? What do you mean?
Yeah, it's TCP sockets.
But it's internal, right?
Yes, it's internal.
The same machine.
That's the magic about KHMU. You can actually configure the network interfaces to whatever you want. You can emulate any network interface that you want, any that is supported, and you can actually configure the network addresses, and you can use it to communicate with each other.
So actually,
that would be interesting and a nice challenge, because it would enable to build kind of a simulator that would be quite close to reality.
actually
if you could emulate, I mean, you could join KHMU instances, simulating some platform with its requirements, whatever they are, and they would be internally or they could be connected via some kind of simulator, network simulator, with some kind of, I don't know, some network.
That's the KhronoSim project actually. That's exactly that. It uses, although it can use some real
network
hardware.
connectivity is still not developed, or what are you?
No, it's already. So basically the KhronoSim project, the goal is to, basically in a closed loop, you want to integrate hardware with simulated hardware in the loop, exactly. And the objective is to test systems.
Okay, so could it be possible to have several instances distributed and have a network simulator connected to it that could emulate some kind of distributed architecture for planes or drones, for instance?
I would say yes.
Because in that case, I would be very interested in hearing more about this, because we have a project, by the way, or we have a project proposal which is still not project, which we could potentially use some technology like this. And the objective is to use distributed architectures that would normally be used in main aircraft, but ported into drones.
Mm-hmm.
So
you don't have the
you still have distributed, it's a distributed architecture with sensors and actuators that can be, and processing units that can be spread across the aircraft. But they would be connected by some kind of a point-to-point network instead of traditional AFTX and stuff like that. Like instead of Wave and kind of goes like that, we would have some peer-to-peer network that would still offer some kind of guarantee. But this would have to be designed by us.
That's also possible. We can have like point-to-point. And even though we didn't try, I think that just because of the experiments that Critical is doing with in the scope of KhronoSim, I think that it's possible to have several CAMU instances in the loop, like connected via a network, with real hardware as well, so it's up to you, and to perform this test. So according to that experiments, I would say that
So how
it's
are
possible.
you still?
Okay.
I'm going to stay here. So.
Actually, Renato is going to continue with us for a few months already. Okay, so thank you very much.
You have a question?
So anyone else has? Okay, of course, you didn't have.
The basic one, I think I missed on slide 22. How many CAMU instances there were there?
22, okay, here. Actually,
What application was with the guest in the host?
the host application was running in normal time. Let me check. Slide 22.
I think. This one.
So, this was actually one CAMU instance, okay?
Okay.
This was on one CAMU instance. It was measured, this was the real hardware, a real computer, which runs the emulator, but you can easily use, I think you could use another CAMU instances, like Ricardo was saying, that could communicate with this one, but in effect, for this to be tested, that machine could not be throttled, because it would not count the real time as well, but this is one CAMU instant, and this is the real computer.
Yeah, so about throttling. So if I have two CAMU instances, when I'm throttling one of them, the second one, can it be affected or it cannot be?
No. That's one of the things that we wanted to guarantee. They are completely independent. Unless you throttle the second one, it will run at the natural speed, the maximum speed that you can using your CPU. So they are completely independent. The commands that you send to one do not affect the other one, which is why you can configure them individually, or you can send a script and configure both.
Okay. Thank you.
Any other question? Okay, fine.
No, just a small correction. The last graph that you showed looked more hyperbolic than exponential. So,
This one?
yeah.
Actually, that's a discussion that me and Renato were having. Because as we cannot go after 100%, we don't know if the graph will be exponential or quadratic.
Yeah, but that's the point. We know that we cannot go, so that's what the hyperbolic is.
Okay. Thank you for the correction then.
Not
Unless there is a logarithmic scale on the left. Which is not then.
Okay, any other question? No? So thank you, Renato, once again. Now we have Rúben and Joel, who are supervised by Oliveira and Pinto, and they will talk about our things on multiprocessor systems or early states. So I guess that you can start now.
Yeah, thanks. So, yeah, our final project from our bachelor's degree in computer engineering talks about the experiment analysis done on the FM's operating system. I don't know if you are familiar with it. So. The introduction of the real-time embedded system world has been introduced to the concept of multiprocessing not a long time ago, and this introduction comes with a number of problems that the developers of the FTOS, the real-time operating systems, must face, new problems, and along with that, it was proposed to us to make some analysis to the mechanisms FTEMS implements on the SMP environment. These problems contemplate the scheduler. For example, it is introduced here a new dimension in scheduling problems. This is the scheduler now, besides having to choose which process to run, it has to choose in which processors to run it. And along with this, the synchronization mechanisms or problems become maybe even more critical because, become even more critical due to the appearance of true task concurrency. And so, there's that. We'll talk about we'll introduce a little about FTEMS and the work with that.
As some of you know, FTEMS is a real-time operating system. It's known for being a real-time executive for multiprocessor systems. It is an open source RTOS that supports application programming interfaces such as POSIX and ITRON. It is also correspondent to the POSIX profile 52 and single process and multi-thread environment having an in-memory file system. Here we have all the managers provided by FTEMS. This is the interface presented to FTEMS applications where we have here the synchronization, the interruptions, output interruptions. Here the signals are the software interrupts that are the ISEP, asynchronous service routines. Here is the rate monotonic. The rate monotonic here is not a scheduler. It is to create periodic tasks, only for the creation of periodic tasks. And in FTEMS core, we have a small set of processor dependent routines such as the scheduling, the dispatching, and object management. Okay, so as Rúben already said, our main focus was to develop FTEMS application to test the synchronization and the scheduling of FTEMS. So now we're going to speak a little about those mechanisms. So for the schedulers, in ADF SMP configurations we have 4 schedulers. 3 of them are fixed priorities, the simple, the deterministic, and the arbitrary. And we also have a dynamic priority scheduler that is ADF. So the simple is a really easy scheduler, a fixed priority preemptive scheduler with a maximum of 255 priorities, only has one sorted chain to the ready tasks. Then we have the deterministic priority, extremely similar with the simple, but differs on the ways it organizes its ready tasks. The deterministic has deterministic has one sorted chain for each priority level. That means that we can have at the maximum 255 sorted chains as the maximum priority is 255. Then in the arbitrary is also extremely similar to deterministic. We have 255 as the maximum priority, one sorted chain for each priority, but this scheduler allows it to have core affinity with the task. Then we can set through to a directive that is FTM task set affinity, we can set the affinity of a task to 1, 2 or 3 processors. And then we have our dynamic scheduler, the EDF, earliest deadline first. It's the only dynamic scheduler supported by FTMs on SMP configurations. It is also the default scheduler. Also allows it core affinity, only 1-to-1 and 1-to-all. As said before, for the use of periodic tasks, we had to join EDF with the rate monotonic managers to have dynamic priorities, since the EDF here can create 2 types of priorities. The background tasks that have tasks that are tasks that do not have any periodicity, that is, do not use the rate monotonic manager, and then we have the periodic tasks that are created with the rate monotonic and are scheduled by our EDF. And then we have the synchronization.
Yeah, so as mentioned before, the synchronization is also a very important theme on related to SMP, and the main difference rely on the use of mutexes, since they provide the mutual exclusion principle necessary. The use of mutexes require a protocol that helps with the operating system deciding what to do when there are access to shared resources. So this is extremely important, especially in latency sensitive systems, because the system cannot have a task waiting forever, especially if this means if it's a high priority task. So something must be done to manage this access and this contendency. Also, in preemptive environments, in multitasking preemptive environments, there's a problem that can occur. I think you're all familiar with it, and that's the priority inversion. So the priority inversion happens when a high priority task is stopped or is it's impedido. So a high priority task is not allowed to run due to the execution of lower priority tasks than this. We have a small example here. In this case, we have the higher priority task, T2, that is extremely delayed. Its execution is extremely delayed due to the critical section that is shared with the T1. So T1, when the higher priority task reaches the CPU, it has to wait for the lower priority to execute its critical section. And this is not very well represented, but these critical sections here are shared amongst these 2 tasks. And so, by being preempted here by a medium priority task, this stops completely. It's an unexpected behavior. So the higher priority stops from executing due to the execution of this middle priority task. Yeah. So the locking protocols also help to control these situations and also deadlock situations. So the FTMs currently offer support for 2 the more recent locking protocols presented, which are the MRSP and OMIP. So the MRSP is a generalization of the priority ceiling protocol. This is a task. We define a ceiling priority, and the tasks that contend to access a mutex have their priority raised to this ceiling priority. The way the tasks wait for access is by a spin-based locking method. This is the task never yields the use of the processor, and this is the defining characteristic of this protocol. In other words, when tasks are waiting to access a resource, they can use their cycles to help other running tasks that could be preempted. This is how the locking protocol goes around the problem of priority inversion. So this is a way. FTEMs also offers OMIP. Both of these locking protocols are not available to dynamic priority schedulers. And so this OMIP is a generalization of the priority inheritance. In this case, and tasks don't have an active waiting for the mutex. It's a different mechanism and a little bit more complex one to implement. And so, in this case, the main idea of this protocol is that it provides a helping protocol like MRSP, and so, but it works in a different way. In this case, the tasks that are holding a mutex and are preempted can migrate between cores and can run on the cycles that other tasks waiting for the resource are using. So it's a different mechanism and it has complications, different complications when it comes to implementing. So there's that. After this,
as I said before,
exactly, to better understand.
So as I said before, our main goal was to develop RTM's application to test the mechanisms that we just explained. But before developing those samples, we had the idea to develop a new feature inside FTM's kernels to help us to understand the scheduler, so be able to verify all the preemptions and to check also if our samples were correctly implemented. Okay, so we have our design of our sample. It should preempt another task, and how we were going to check it. Are we going to see if it migrates? Are we going to deal with that? So the idea was to develop a buffer, a circular buffer. Our new feature will be that will store the 1,000 last preemptions inside those structures, as can be seen here. This buffer is initialized with the executive initializer of FTMs at the same moment as the others managers and data structures. The allocations, the preemptions, is stored when we are allocating a processor to a thread, and we're going to store the ID of both leaving and entering thread, the moment, the tick, the processor in which it occurred, and then the rest is just printing information here. And for the printing, then to obtain our results, we developed a new FTM directive that allows us to get the information directly from the kernel.
Yeah, so we implemented some test suits. We have some examples next. But these target specifically the scheduling and the synchronization mechanisms that we awarded. The OMIP helping protocol was not implemented due to the documentation of FTMs not being very explicit on how
to use it.
Not really how to use it, but even in the state of the implementation of this protocol. So it's kind of a tricky situation here.
So then, okay, for scheduling FTM application, our test suite. So here, first, to show, here we have a result from our buffer, where we can see the leaving, the entering thread, the process in which it occurred, and the time. In this sample, we tested the arbitrary core affinity scheduler. So we created a really simple sample, a real simple application, where we were going to play initially with the init task, that is the task that is configured to enter first to configure the application, is the main thread application. We're going to play with them, moving it around from processor to processor, and so on. So here, our vision will be this one, initially, until here. So we have the init task on the last processor, we're going to move it to the first, the second, to the third, and then it's going to be back to the last processor. Also, we were going to play with the affinity of the task. So we're going to create task 1 and 0 and set them on the first two processors. Later, we were thinking of creating another task, TA2, at this moment, and set its affinity to the processor 0, 1, and 3. But the trick here is that TA2 had a lower priority than TA0, TA1. So we have here a free processor, CPU2, but TA2 isn't allowed to run on that processor, only on the first two and the last. So the last we have here the init task. The init task is a non-preemptive task, so we already can forget processor 3. It won't enter in the processor 3. So our main two options was to set its priority with a directive offered by the task manager of RTMs, that is RTM's task set priority, and we've done it, to later, here at that moment, set its priority to finally preempt or CPU 0 or to enter or CPU 0 or CPU 1. And here we have what I just described, our results, to compare with our diagram scheduling to verify if it is correct. So, as you can see here, the 97 is the init task that is moved to CPU 0, then here to CPU 1, here to CPU 2, and here finally back to CPU 3. Then we create the task TA0, and TA1 that enter CPU 0 and CPU 1. And here we can see at tick 31 we created our TA2 at moment 31, but it only enters the processor CPU 1 at moment 71. That's when we set its priority and only preempts at that moment. So it won't enter the CPU 0, that is the CPU 2, that is the unoccupied processor. And here, here is just the configuration of the scheduler, of the arbitrary processor affinity scheduler.
Yeah, just a small example from a test suite related with the synchronization. I don't know if it was clear, but the test suites revolve around the configuration information and then the whole task or the sequence of executives. So in this case we must configure the number of errors. All this configuration is done by the developer, so we must configure the number of errors that you're going to use on the application and so on. And the idea of the task, we don't have the output here, but the idea was that the task would be just performing a simple wait on the barrier, and the directive of the barrier, like the weight and the creation of the variant and all the configurations are tested on this sample. Yeah, so in the end we came to the realization that there are not many case studies in SMP real-time systems, so we ended our work by adapting a famous case study in the embedded world, of course, to our execution environment. So this case study contemplates a mind control study. This is a system that controls the motor of a pump that is meant to retrieve water from a sump, and this control the system has over the pump motor is also controlled by the environment aspects of the system. So what this means is when the water reaches a certain threshold, this level will be read by the sensors. By the high-low water sensors, and this sensor should be able to turn the pump on or off according to the CH4 sensor readings. This is if the CH4 level are above a certain threshold, even when the water is meant to be pulled from the sump, this can't happen because the levels are not safe to operate the motor. So that's the idea. And so the methane level the CH4. The CH4 is methane. So is actually. I'm sorry. I'm kind of. The CH4 sensor also has the ability to turn the pump off, only off, not on. Because if a critical value is red over here, there's a deadline associated with the turning off of the pump. So this is kind of the critical part of the system. So the CH4 captures a critical level. It must turn the pump off. And also the idle water must function with this model.
So this interaction between CH4, so the methane, and the idle water sensor will be further explained with other diagrams to better understand. Another thing is that the monoxide, carbon, and airflow, and CH4, water flow, and idle water sensor, all of them will send alarms in case of dangerous readings to an operator. So.
We ended up with this task set.
First, both 5 of them will be simulated as periodic tasks by our system. We don't have really sensors in our hands, so we simulated all of that with periodic tasks. For that, here is the information about our periodic tasks: the period, deadline, priority, and the case execution time. The worst case execution time. The deadline, the priority was assigned with a deadline monotonic priority assignment policy that is inversely to the deadline. And before implementing our case study, we had to verify if our system was schedulable. So we used this famous response time analysis test for schedulability for fixed priorities, where we calculated each response time for each task. And our system will be schedulable if each response time will be inferior to its relative deadline. We forgot to say. We use the deterministic priority scheduler to develop our system.
Yeah, we discarded the use of the default scheduler since the default scheduler contemplates dynamic priorities, and that is not supported by the current locking protocols implemented.
With the implementation of our system, we reached 3 points. The first one I will speak is the constraint deadlines. RTMs does not offer constraint deadlines. It only has implicit deadlines. So for that, we have deadlines, as you can see here. So how did we turn around this problem? We decided to use timers to alert us and to stop the application when deadlines were missed. That was our way to turn around that problem. Another one was, as I said before, ISER, asynchronous service routing, are the signals of RTMs, the software interrupts. And initially we wanted to use them as on a processor. The case study initially for a processor used interruptions, software interruptions. So we also wanted to use them. The main problem is in RTMs, they are asynchronous. There is the handler, we only handle them when it entered the processor. Sadly for us, that was a problem, because we will lose a little bit of our critical situation to turn off the pump when the methane level are critical. So we have to turn around the use of asynchronous service routines, and we had to use states. Our focus was to use states to turn around the software interruptions, and then also to send the alarms to the operator. We decided to use message queues that already offer us a little bit of synchronization, so we didn't have to worry about that.
Yeah, so these are the diagrams that represent the states in which the pump can be, and also there's the state related to the CH4. So if it is safe or not to operate the pump, and if the pump is on or off. So the high-low water sensor is responsible for changing the state of the motor. Also, when turning it off, it must ask the environment section if it is safe to turn off. So that's the idea. By turning off, it can turn off automatically. I mean, immediately, but when turning off, it has to check for the requirement safety.
You have to check for the environment system to turn on the pump.
Yeah.
Turn on the pump. And then here we have our situation to turn off the pump when methane level reading is explosive. It's above the threshold. So here the CH4 sensor will simulate our reading. If the methane level is above threshold, we're going to check first. We're going to send our alarm to the operator and then check the present state to change it and then verify if the pump is on. If the pump is on, we're going to change the state of the pump. If it isn't, we don't have to worry about it. Only set
these
the
checks on 2 and 3
methane states.
are actually for performance reasons. So if the state is already off, there's no need to turn it off again. So it's kind of just a check that is represented here and turns this diagram a little more complex than it actually is.
Well, thanks for hearing us. This was not a very good prepared presentation. We didn't have much time, but that's what we made it. So, any question?
So, who has questions? So, caution.
I think it was slide 12, when you were explaining barriers. So if I understand correctly, that I have to specify in the pragma the number of barriers that I'm going to need.
Yes. You have to configure everything. The number of processors, the number of semaphores, the number of barriers. You have to configure everything before.
Yeah, this is how the application development works.
So this is basically the common practice. It's for any kind of primitive, like you were saying, for any kind of synchronization.
Yes, it's because the nature of the own operating system, I guess, because it's an open source operating system and it is used for several purposes, not a specific one. So this is the way they kind of develop the application development.
Yeah,
The developer configures everything.
Sometimes it's really tricky. You have to really configure everything, and you don't have the documentation about it. You can read all the documentation. They don't say if you need the configuration for message queues and all other stuff. They don't say anything.
Basically, you are describing an open source.
Yeah.
Actually, with Artems is well documented. You cannot complain about that. And when compared, for instance, to Camo,
Yeah.
Artems is very well documented.
Very, very bad.
Yeah.
Hammer it down.
I think that it's because you need to know offline what you are dealing with. So basically you are specifying exactly what you, how many semaphores you want, how many barriers you want.
Yeah, for
Just
example,
because
when using message queues, you also have to specify the memory that you're going to use for each message. Yeah.
I think that it's because you want it deterministic and you want to make it deterministic at compilation time, so that's why they make you use this kind of configuration just to make sure that.
And not only completion time, but also link time, because when you're choosing your scheduler, it can be chosen at link time. So all the configurations you have are really assumed at link time for the scheduler. So it assumes all the configurations both at compilation time and at link time.
Okay. So linking is part of compilation.
Yes.
Thanks.
Parts of process.
So it's part of the process, exactly. So when I was saying compilation, I was including all parts of the process.
No, it's not really a question regarding the presentation, it's mostly general about Artemis. And it's, well, can you use it in platforms in which resources are very low?
The last test that I did was using this STM32F4. So it's not like a
STM32, that's
M4
M4 processor.
or M4 processor. Know exactly the frequency of the processor, but I was doing some experiments with that board and it was okay. I mean, it was working. I mean, at least with the sample applications that they provide.
No, it's interesting to see that it's
They were using the emulator for the testing purposes,
You forgot to mention that we use Camel.
Yeah, they were using Emu as well for to emulate the board where they were putting their application and their suites to execute.
Maybe it could be potentially interesting to have a training session regarding our times.
Okay.
And eventually regarding Camel also. It could be interesting.
No, that can be done. If there are enough people interested on that can be done.
There sure is. And for sure. We force people. No, I think we should have it.
Okay.
And maybe even free RTOS. I don't know.
Actually, the purpose of their
Free RTOS could also be interesting.
actually the purpose of their work was to gather information about Artems because we at CISTER we will start a project
System, it seems rather nice.
that has a focus on that.
By the way, just a quick question regarding the support of those locking protocols. I'm not sure that if there are many operating systems that support those in EDF.
Yeah, that's
Yeah,
I'm not sure.
Yeah,
If you know
exactly.
anyone.
Exactly.
Currently,
Currently, I don't think there is actually a very efficient protocol proposed to the
I don't think so.
hence maybe I didn't make that clear, but hence the lack of implementation for the schedule.
Gosh.
Yeah, the circular buffer, I didn't get, is it like the data structure, it's like a list or something? How basically those nodes?
yeah. They basically like a list. So
Yeah,
it's
Okay,
always
then it's fine.
It's a
You don't need
little
to-
Any more questions? So I would thank the speakers once again and thank you everybody for being here.
Thank you.